you for coming to class today. So we have a really amazing work in store for you guys. So this was work done by Stephen Zong as well as his team from Salesforce, and David Parks was actually also on this paper. Yeah. So I think the first thing we're going to do is watch this video that they made for us. And if you guys are curious about the paper, you can click on that, and then the left one is a blog about it.
Let me connect the.
Is there a separate audio?
We should switch. Sorry?
Can you just play out from your
Yeah, I can just crank the audio up and put it on.
Yeah. Let's see whether.
Salesforce Research, we seek to build AI that positively impacts the world. We created an AI framework to design economic policy. We call it the AI Economist. Economies revolve around people who focus on their own outcomes. For example, by gathering resources, trading, and building to earn income. Economies are part of broader societies. Across societies, governments tax and subsidize to promote their own socioeconomic objectives. In our experiments, we focus on economic equality and productivity. But how should tax policies be designed? If taxes are too high, people's motivation may suffer, hindering productivity. If taxes are too low, equality may suffer. Using reinforcement learning and economic simulations, the AI Economist designs tax policies to achieve equality productivity goals set by the government. In our simulations, AI agents pay taxes, while the AI Economist recommends how to set taxes. It also advises how to subsidize and redistribute wealth. Here is one of millions of economic simulations in which AI agents collect and trade wood and stone and build houses. We compare many simulations where the AI agents and AI economist continuously learn to adapt to each other. Each AI agent trains to maximize its own monetary outcome, while the AI economist optimizes social welfare for all. In our experiments, the AI economist improves the equality productivity goal over tax models like the free market and the SIAS model. For now, our simulation is still relatively simple. Realism, scale, and computing power will continue to advance over the next years. Eventually, people can define wide ranges of social welfare goals like sustainability and use AI economist policies to achieve them. Imagine what a future AI economist trained on the equivalent of millions of years could do to support better policies in the real world.
All right, great. So I think that gives somewhat of an overview of what the AI Economist is. The next slide. So the first thing we're going to talk about today is the motivation behind this work. So there's a few things here. So there's an explicit definition of incentive, right, that we can get from this work in terms of like, we can really say like what individual agent, what their incentives should be, which is to maximize utility. But we could also say at a high level for the principal agent what theirs should be, right, like maximizing social welfare. But the issue is that like, when we have this kind of thing, it's very hard to actually do in practice analytically. So when when we can't really simulate this, or when we can't really write down the equations, then we can't really derive a closed form solution either, right? And so this paper is taking a first step towards this, where we could potentially use some tools from AI and CS to solve these intractable problems in, like standard traditional economics. So some things that we've previously covered in this class are, the idea of a well-defined rational agent, and then collaborative learning, so the federated learning having different trainings on every single individual device. And then we've also talked about how we could potentially use deep learning for mechanism design. So this paper will cover a few topics from each of these areas. Yeah. So this first point goes back to what I was saying earlier. We want to design this global macroeconomic policy, but doing so is very hard to do, right? And so we can frame this problem as a large-scale mechanism design problem, where we use a mechanism that's thought of at a much larger scale than the mechanisms that we typically think of, right? So usually when we think of a mechanism, maybe it's for like an auction or a market or something, but here we're really going to try to simulate the entire economy. So the issue is that traditional mechanism design methods have significant limitations because they don't typically try to tackle such a hard problem. And so in this case, computational approaches offer promise. The issue is that there hasn't really ever, before this paper, there wasn't anybody who had really come up with a way to do this, like using the compute that we have now in a mechanism design framework. And so that's what this paper fills. Yeah. Okay, right, so the first thing we want to talk about is what optimal tax policy is. So the question is, how do we, if we're trying to plan for the entire economy, how do we ensure social fairness and equity while also maintaining agent morality and economic growth? So it's really a constrained optimization where we have this kind of Pareto frontier between the social fairness and equity, constrained by things like how we define morality and economic growth. So we want to ensure that there's maybe some base economic growth, but also that there's equity amongst all of the participants in this economy. So the key challenge is how we balance this. And the idea is that if we didn't have any tax policy, then maybe this would become a very the Gini index might become very low or something, and so it'd be a very imbalanced economy. And then how do we build this mechanism such that it's robust to agents trying to game it? So for example, if I had all these different tax brackets, maybe I'll try to get just at the barrier, in between two tax brackets, so I get taxed less, right? So in a typical economic model, there's so many ways to game the current U.S. tax system, and this is a very known thing. And so the idea is that, well, if we can build an agent that actually can respond to this, right, and is dynamic now, then maybe this can help with gaming. And so this has to do with our last point here as well. So the first thing we're going to talk a little bit about is the environment, or the second thing is the environment and the setup. So I'm going to give a brief introduction to reinforcement learning because we haven't covered this so far yet in class. This is my primary research area. So there's been, I think the biggest success, or the most famous success from reinforcement learning is this program called AlphaGo. So back in 2016, DeepMind created this program that beat the world's best player at the time in Go. And so the world's best player at the time was Lee Sedol. And what was really fascinating about this is that there was emergent behaviors that came out of this program, even back in 2016. So this is a very famous move. This is called Move 37. And this move, the experts, the analysts looked at it and they said, this makes no sense, right? So according to regular human intuition, it was this would be a terrible move. But it turned out to be instrumental in its win, 200 moves later or something like that. And so this was really this beautiful example of emergence. And what we hope is that we can capture the same kind of novelty in maybe this mechanism design problem. The reason why reinforcement learning is able to do this is because unlike traditional supervised learning paradigms, we don't actually specify what the model is supposed to do, right? We just specify the goal for the model, and we don't specify how it can get there. So if there's some way that it finds to get there that doesn't follow human intuition but is better than humans, then the model is going to optimize for that. And so this is the dream, right? This is the hope. So there's other examples like StarCraft, where they actually created a multi-agent RL setup, and they had a different agent for all 5 of your players. And they weren't able to like get to the very best performance here. They weren't able to beat every other human team by like a long shot, but they got, I think, up to like the 99th percentile. So this is another great example of how powerful reinforcement learning can be. And then recently there's a work that's been published by DeepMind called Gato. So Gato takes a lot of the intuitions that we learned from large language modeling, which is basically if you train it on a lot of data and you use a lot of compute with the transformer, you're going to get great results. They basically took that intuition as just like, let's do that in RL as well. So you can see here, they train on all these different data sets, like including Atari, Majoko, and even like images, right, and language modeling. And they find that if you just do this and you train on all of this diverse data, you can still get a model that performs at like 70 to 80% of an expert capability on all of them. And so, this is like an idea that maybe we should just scale data and compute as much as we can to get good performance, to get generalist performance. And then, so the next one is even ChatGPT is an example of, the power of RL. So ChatGPT uses something called RLHF, reinforcement learning from human feedback. And so the idea is that first you train using self-supervised learning this very large language model, and then afterwards you can then go and optimize this against human feedback. So they train a reward model that simulates what a human's preferences are, and then they use this new reward model and optimize the old LLM against that. And so this is really how we can get this like controllability and instructability of GPT. And so the next thing will be the Terminator. Okay, so let me give a brief introduction to the formalism of RL. So the main object that we look at in RL is called the Markov decision process. So the Markov decision process comes from just a typical stochastic Markov process, but we add two things. So the first thing that we add is this reward. And then the second thing that we add is this action. And so what we have here is this setup where we have an environment which stochastically outputs a new state and a new reward at each time step. And then the agent will go and take an action given that state. The goal for the agent is to try to maximize the total amount of reward that it gets. So the sum of all the reward into the future discounted by the time step, so that if we have an infinite horizon, the sum doesn't explode to infinity. So what this agent's effectively going to try to do is get as much of this reward as possible. So the way that we specify what to do for the agent is through this reward, and then the environment is how it interacts with the world. And this is, so this is like the typical RL setup. So it's important to note here that both the environment and the agent are Markovian, and this is why it's called an MDP, because the agent only takes in the current state. It only needs the current state to take the action, and the environment only needs to predict the next state and the next reward given the current state and the current action. Sure, we should go back one step. So and then people have extended this to deep learning. So in deep RL, we have an agent that has some data set, and then we parameterize this agent with a policy network, so with like a deep neural network. And so this is the setup that's used in AI Economist. So an RL agent there's a lot of different ways to create one. In this paper, they use something called a policy network. You also could create something called a value function, which tells you how good each state is. And so AlphaGo does this. They use a value function as well as a policy network. And so the value function tells you how to act, right? And so you can immediately extract a policy from any value function by just taking the argmax of any action, for this value function. So like if I had 3 actions and then the first action gave me the most value, then I always want to take that one. And then finally, you could also have a model, which is, like the agent's idea of what the environment should look like. And this is useful if you want to plan several steps into the future, right? So you could say, what if I took this action? Where would it take me? What if I took that action? So this model is another thing that you can include. Right, so this policy is a map from state to action. You can have either deterministic or a stochastic policy. So for a deterministic policy, you just go from state to action. This is the same as a strategy in typical game theory. And then here we have pi of A given S, which is just the probability that you take any action in a given state. Right, so this value function that I was talking about earlier, it's exactly the sum of discounted rewards. And then we take the expectation of this over the policy's behavior. And so it's important to do this because it's stochastic, right? All of these r's are random variables here. So if you have this, then we can see how good each state is, and we can choose which action to take based off of that. And then finally, this model that we could potentially put is just this probability of next state given the current state and the action. So you could try to estimate this, with like Monte Carlo or just with like an empirical estimate or some other fancy thing. And then if you had this model, then now you can like maybe take several actions in your head, right? And then try to figure out what the best thing to do is from there. Yeah, so that's our 3. So to give a quick, simplified example, like a toy example of what an RL problem typically looks like. So here we have a maze where you want to go from this start state to this end state, and we're going to try to get the agent to get to the goal as soon as possible. So at each time step, we're going to give it -1 reward. So to get the maximum reward here, it's going to try to get to the goal as soon as possible. So the actions it can take are up, down, left, right, and then the state is where it is. So here is an optimal policy for this. And so you can see this is a map that goes from each state to an action. Yeah. And this is what the value function would look like, which is how much reward into the future it should expect to get. So there's some of discounted rewards. And so now we want to ask sort of the question, what makes RL useful for AI economists?
Does anyone have any suggestions?
It's generally hard to get supervised data in these kind of settings. So obviously, it's easier to say whether a decision was more beneficial or not, so it's easier to rate a decision rather than give an explicit good, bad, ground truth kind of estimate.
For sure.
Yeah, I think that's a great point. So in RL, right, we only need a reward function. We don't need labels, which typically is much easier to get. And as we saw on the very first slide, right, in this class we have some very well-defined notions of what incentives are for agents and for policies, so we can directly use those as reward functions. Does anybody else have some ideas?
All right, we'll move on then. Yeah, we'll start by covering kind of like going into the paper after Eddie gave a great intro of reinforcement learning, kind of the high-level environment dynamics. So the nuance of this paper is it has 2-level reinforcement learning. And specifically what that means in more plain English is that we have at the top level this mechanism agent, which is trying to learn this tax policy to maximize this quantity of social welfare, while the tax agents kind of operate within that paradigm where they're trying to learn their own optional agent actions, like how to interact with this market, this real world environment, trying to maximize their own personal utilities. And so some rough details about the actual simulation. So they occur over episodes of 10 tax periods, each of 100 days. You can equate a tax period to a year in our real world taxation. And so per tax schedule, basically the mechanism agent will read kind of the inputs to its own policy and then update whatever the tax schedule should be. And then per episode, just as a training detail, the mechanism updates the policy per episode. And so the other thing to know is that it's a closed economy, not quite like our own, in the sense that all the taxed income is just then equitably redistributed, so no money ever leaves the economy. So going to the agent dynamics, Eddie talked about how our reinforcement learning agents need to optimize over a quantity. So we have the agent's utility function over here. It's a little bit of mathematical notation, but essentially what it's saying is that each agent is trying to maximize the expected discounted return of its utility, where its utility is this isoelastic function at the right, which basically, in more qualitative terms, it basically models kind of diminishing return over more money. So having more money above a certain period will not grant you the same utility as if you had no money. And then it also models kind of the linearly decreasing utility as you work harder. So you don't want to work as hard as you can, right? And so kind of each agent is trying to maximize their policy with respect to the actions that they can take, the actions that this negative I means the actions that other agents in the system can take, and then also over the next state that the mechanism will provide. And so in terms of the agent's action space, there's a lot of actions that they can take. Simplified, there's movement across the game board to acquire things like resources, as we saw in the video. There's a complex, I think, continuous double auction where they can buy and sell resources. And then they can also choose if they have good labor to, or in any case, to kind of build houses and like expand their income that way. And so like I think the key crux that actually makes this problem super interesting is the trading, this continuous double auction, and the fact that I think agents' interactions can strongly affect their optimal policy. In terms of the mechanism dynamics, so this is what the mechanism utility is trying to optimize for. Instead of optimizing for individual agent utility, we can see it just replaces it with social welfare, where at each like action's immediate reward is kind of the difference in social welfare that action granted. And so in the paper, they use two examples of social welfare. One is on the top. The top one is linear weighted sums of agent utility, where basically the weights are selected to be 1 over the agent's income multiplied by their own personal utility. And then they also use this other one, which is directly mentioned in the video, this idea of the equality productivity product, which is kind of like this Pareto frontier that Eddie was talking about. What the model's actually outputting is the inputs of this bracket taxation mechanism. Basically, it's very similar to kind of like how our taxation mechanism works in the real world, but you fix a number of brackets, and at any point the model is outputting kind of the proportions in which to tax, or the levels in which to tax each bracket. And so in the paper, we also discuss kind of, or the authors kind of discuss also some alternative planar baselines. They discuss, I think, free market, so i.e. no taxation, where productivity is maximized and there kind of is maybe no incentive for equity. They mentioned the size mechanism, which is kind of this more theory-heavy framework, which assumes some hyperparameters that you regress from income data, and then it uses those, it regresses some kind of elasticity, which then you can use to derive an actual taxation mechanism. And then they also compare it against the US federal mechanism, which we'll dive into later. And so to kind of understand the policy inputs based on like what Eddie talked about, I think from the agent side, basically what their inputs are is they get a limited vision view of the board, as well as some public inputs, semi-private. So what this means is the inputs to the agent are the anonymized incomes of everyone else in the system, as well as their own private variables, like how good they are like how much labor they're doing, as well as how much skill that they have in a certain, in building. And so they'll pass that through a model, and then it'll output a probability distribution over actions to take. And then similarly for the planar model, it doesn't consume the map itself, but rather just consumes the public state, as well as, again, this anonymized income, and then outputs this, like the actions in which, how to set the payment brackets. And so again, like going into the flow, I think to emphasize the kind of the non-stationarity of this problem is that kind of the flow is the planner is observing these inputs and deciding this tax rate, which then feeds into the utility or the reward that the agents decide. So you can imagine that if there isn't kind of some nuance in learning these together, that if the planner doesn't know what it's doing, then the agents have kind of a moving goalpost to optimize against. You can see kind of like some of the dynamics of the game down here as well. Basically, there's exchange of materials through this auction and exchange of income, as well as certain agents deciding to build, certain agents deciding to gather. And then on the right, you can kind of see from the paper kind of what the welfare looks in different situations when we have the effective tax rates of different agents to be different. And that's all able to be manipulated through the planner deciding this taxation schedule. So I guess we'll open another question. I guess like from your guys' reading of the paper, were there any like modeling choices you found were like interesting, strange? How did you guys feel about the soundness of the model and like any changes you guys think you would make? We'll take hopefully an answer for each of these.
Okay, I don't think it's like something wrong to me, but maybe something that I'm a little confused. So for me, I can see like for agent and the mechanical learner, like they do have like different observability of things.
Mm-hmm.
So does that mean essentially they actually have different state space when they know the RL problem? But if they have different state space, how can they actually incorporate into one RL problem instead of like two independently? Or they do share the same state space?
Yeah, so that's a really good point. So I think the way that maybe it's simpler to think about, you should be thinking about them as like a combined like two-level RL problem, but in some sense, the environments that each is dealing with is not the same, right? The agent's kind of environment, they have their own action space, which is like kind of setting these tax brackets, versus the agent's action space is like, what action should I do? And so in some sense, these are two separate environments, but the dynamics are kind of intertwined because this is a single economy, right? Does that kind of answer that question?
Yeah, I think kind of. I'm just not pretty sure about like how they actually do the thing. Like maybe
Mhm.
it's similar to.
Sure, hopefully we'll cover that in more detail, which will make more sense. Any other bits people found interesting in terms of the modeling side?
I mean, I understand that it's more complex than a lot of like tax policy
Mhm.
research that's been done before, but they also put the disclaimer that like our research using gathered trade bill can't be used in practice. So I don't know. I found that part interesting.
Mm-hmm.
We'll talk about that a lot too in a second here.
All right, one more before we go to the next slide.
Is there any ideas about how we might potentially improve the modeling based on what we've seen so far? So yeah.
Do you have any intuition if like you could incorporate like a bounded rationality thing, or like with some probability they actually don't take the right action? I mean, it's kind of there in like it's actually being stochastic, but I wonder if there's like a more like a formal way of incorporating. Because like if you have like a large set of agents, there's some probability that a lot of them might not be exactly rational and do whatever is maximizes the agent.
Yeah, I think that's a really great point, and I agree with you.
Yeah, just add on to that, like people on average are irrational, and that's not the assumption that was made in this paper. It was like rational with some stochasticity.
You're saying people on average are or are not rational?
Are not rational, are irrational.
Okay.
I'm a little bit confused about like the second or the top layer of the two-level
Yeah.
RL. Like, is why we want that to be RL? And
Right. So the idea is that we want a dynamic planner. So we want something that responds to gaming. Yeah. If it was just a fixed thing, then or are you asking why don't we just optimize?
yeah,
Like solve the so there's no closed form solution in this case. Yeah. Just because the environment is too complex. Yeah. So to give a quick like example of how this like one like tax period would work in this game. So here, right, we have episode N where we have, this first guy has 50% tax and then the second guy has 20% tax. So you can see here, the first one makes 100 and the second one makes 200. And so this guy gets to keep 160 coins and this guy gets to keep 50 coins, right? So then this is what the social welfare looks like. In the next episode, the planner then goes and changes these rates based on trying to optimize for the product, like this area here. So then it changes the first one's tax rate to 22% and the second one to 39%. And so you can see now the second guy gets to keep more, and or the first guy gets to keep more, and the second guy has to give away more. And so you see the social welfare has increased. So this gives you some idea of like what each time step looks like from the social planner. And then in between each of these episodes, like these two agents will take 100 actions to try to maximize the amount of coins they get, minus like whatever linear effort they put into.
Yeah, so those were a good set of like things you guys found interesting. I think for us on the more technical side, I think there are a couple of quotes that we pulled from the paper that we found especially interesting. I think the big theme were kind of just in the paper is the idea of sample inefficiency. I think if you actually distill the numbers, they are conducting approximately like 100 million tax years of sampling, which is quite unrealistic, but we'll touch on that later. And specifically, I think one point that we found interesting was kind of the choice in like how big the batch sizes for each learning step need to be as you scale the number of agents larger, which kind of reflects like maybe some unscalability with more agents, and so something that could be a very cool future direction. The second thing we found very interesting is that each of the agents in the model were not parameterized differently. They were actually a single shared policy, with the rationale being that if the single agent policy network is able to observe different things, its own like unique strategy can be captured and just conditioned on by what it sees. And so we found that a little bit interesting, just because it's assuming that every agent also learns from every other agent's experiences as well. So some other food for thought. And then the last bit we found interesting, a little bit nuanced, but basically they tuned the environment hyperparameters to align the income distribution, similar to the US federal tax like income distribution in the 2018. We assume part of this was because they wanted to like compare the AI Economist to the US taxation baseline, but it seems a little bit interesting just because you'd expect that the way that you're trying to manipulate this income distribution is also through the tax schedule. So if you're tuning that as a hyperparameter, in some sense it might feel a little bit like cheating. But some other bits that we found interesting. In some sense, we actually, this is like a side note of research, but other bits we found interesting about their modeling choices. They published uploaded two versions of this paper, one in 2020 and one in 2021. And then so some of the circled bits are kind of the hyperparameters that they changed in different versions of this paper. And so I think the general themes that this distills down to is that I think they probably realized that one is, if you look at the learning rates, the agents are always learning faster than the planner. I assume this is like to make the objective kind of more stationary and more tractable. And then the other bit is that given that this faster agent learning, we see differences like the phase 1 training and the phase 2 training. To like recap kind of what the difference between these two things are. The phase 1 training, the agent policies, they're just trained from scratch. So you don't have a mechanism agent kind of trying to learn a tax policy. They kind of just learn from a free market economy. So just learning how to operate in the economy itself. And then in phase 2, they actually learn in the presence of taxes. And so you can see that basically, as with like the second version of the paper with the agents learning much faster, I assume this means that the phase 1 training can be shorter and doesn't have to be as long. And the other bit is, I think, the interesting difference, which we'll cover kind of what this method actually is, but the entropy regularization kind of increased from this first version of the paper to the second, probably indicating that maybe agents needed more exposure to random tax rates and kind of more diverse experience to actually learn more properly.
There's two other points I want to make quickly. The first one, you see they have GPUs, but the second one they don't, which was really surprising to me. I would have expected the second one to have more GPUs. And then the second thing is that they use PPO as the base RL algorithm, which in general is like the most widely used RL algorithm. It's known to be very sample inefficient, but fairly stable.
Nice. So we'll go into some kind of key assumptions and some more high-level details. We can talk about some technical assumptions. I think, as we mentioned, they heavily assume that two-level RL is tractable, which they show us to be true. And just the idea that generally both of these policies can converge even when one of them is providing a non-stationary reward to the other. In terms of economic assumptions, they assume that like this two-level RL captures like economic realism and economic correctness. They show some results, which we'll talk about later, how they validate this in a one-step economy, where essentially they have each of the kind of sub-agents and the tax planner. So the tax planner will set a schedule, each of the agents will optimize, and they'll kind of like run that game multiple times just in a single step, rather than their multi-step. So the second point, agent interactions are kind of analogous approximation to the real world. They show this through like, I think, trying to create this market, which is as like continuous double auction market, which is as realistic as possible. And then the final bit is, I think, with their conclusion, they somewhat assume that like these systems of 4 and 10 agents are kind of enough to make initial claims about larger agent systems. I guess throwing it back to the audience, like any assumptions that you guys found in the paper that were maybe unrealistic or questionable?
I think it's interesting that, like, even though they're doing multi-agent RL, like, RL is their own consideration for multiple agents. Because usually multi-agent RL, the applications are hundreds of agents.
Mm-hmm.
So just the fact that they're like limiting is interesting. It's like an interesting choice. And it would be more interesting if they could generalize the simulating to more agents. So you could have like asking them to think further and see what version you can use for the
Definitely. Yeah, so some, I guess, unrealistic ones that we found, I think, again, the theme of sample and efficiency. I think one of the bits that we were interested is like kind of like what is also the social cost of like doing anything close to this level of taxation sampling. Like, I mean, like you're probably ruining some like sub-agents, so there's probably a difficulty in terms of doing this in the real world. Two is exactly what you said, kind of these multi-step, multi-agent systems of only 4 or 10 agents. They introduced this like high level of realism through this continuous double auction, but if you think about systems of 4 agents, this auction is likely not that actually deep, and so I think the realism of it is like certainly a little bit questionable. And then the last part is we'll talk about kind of like what this strategy actually is, but they have a little bit of an unrealistic curriculum learning where the agents kind of, in addition to just learning this free market, they eventually learn a state where they're being thrown like random tax rates, and that's kind of unrealistic, and there's also an additional social cost with that. So now we'll kind of like go into the training objectives as well as talk about kind of like the training techniques they use. And kind of the big theme of this section is like how did they solve this 2-level RL instability? They had a couple approaches. One was 2-phase training. So in phase 1, you train these agent policies from scratch in a free market. And then in phase 2, they learn in the presence of taxes in the beginning in these random taxes, and then towards the end, kind of with this actual learning tax agent. Specifically, they also have 2 techniques that they mix in with this 2-phase training, specifically curriculum learning. So the idea of like, how can we better like warm up these agents before like letting them evolve with this tax planner over time? And another bit is entropy-based regularization, which is how do we continue to incentivize agents to still explore and avoid just kind of like being set and converging before like maybe a tax schedule changes and they actually need to be adaptable. So curricular learning. So basically this is the idea that we can stagger agent and planner learning to let agents adapt to a wider range of random tax schedules before the planner actually starts to learn. This again goes with the general theme of like staggering this agent and planner learning. Specifically what they do is gradually introduce labor costs and then taxes in a similar step. And so they first start, I think the first curriculum that they do is that they kind of reduce the utility cost associated with labor. And so this is basically trying to incentivize the agents that like, hey, building is okay, versus some of them might invest too much in labor, experience such a strong negative utility that they might not even try labor ever again. And so this kind of goes back to Eddie's point where because RL assumes so much unstructure, you kind of have less control over the signals that you give to agents. And so strategies like this are kind of useful in terms of coercing the agents to more optimal behavior. The second curriculum that they use is kind of this, they remove the maximum marginal tax from the planner side to avoid the planner from like setting too high marginal taxes and kind of like then again providing a significant level of negative utility to the agents trying to optimize. And so this also helps improve stability. And then the kind of third learning curriculum that they use is that they remove, at the very end, they kind of remove the level of planner entropy regularization. What this means is they basically allow the planner to kind of like converge to a actual tax schedule rather than with the entropy having it continue to like be ambitious and like explore new kind of actions.
Yeah, so I just wanted to make a quick point. I think the intuition for the way to think about this is that, in the first problem, before they add all of these fixes, you can imagine your policy landscape where your domain is all the possible policies, and then your y-axis would be like the return that you get on these policies. And what you'd see is like something super bumpy, right? Like there's all of these local minima. And when we add this entropy regularization that like decays, and we add this curriculum learning, and we also add the idea that it should adjust a bunch of random tax rates and all these other things, then what we're effectively doing is smoothing this policy landscape so that it converges to something that they think is more global. And the benefit is now we can converge, but the downside is this is like, you can argue is highly unrealistic.
Yeah, so we kind of touched on entropy-based regularization, but this is essentially the quantity that you'd be adding to their objective. It's the negative expectation of the policy's log probabilities. And so you can imagine basically qualitatively what this means is that the smaller your probabilities, the higher this entropy quantity is, meaning that like agents who are less sure of their next actions, like that behavior is rewarded. And so that's essentially the intuition behind this technique, and kind of we touched on like how they employ that in this like scheduling. So now we'll touch on the results, I guess, before we dive into kind of what we found interesting. I guess, what did you guys find interesting from the results?
Quick question, what you earlier slide about entropy.
Mhm.
Couldn't they also control this via PPO, like essentially linearize and deviations from earlier strategies better?
Can you say that again?
The like stuff that you're doing here about entropy, couldn't they also like control this kind of problem using PPO, like by tuning some of those hyperparameters?
So I think PPO's main hyperparameter is like how large the trust region is, right? Like how much they clip by. That's a little different from the entropy. So the entropy would encourage seeing more exploration, but the clipness is just like how much to change the policy in each step. So I don't know if there's actually an entropy hyperparameter in the original PPO. So SAC does have this, but that's like completely different. Yeah.
Yeah, anything anyone found interesting? Could be small, big.
I mean, I think some like what they covered in the emergent phenomena section about like the high energy gaming, or there's also the trade-off between like equality and productivity was interesting.
Exactly. So yeah, that's actually one of the points that we'll touch upon. I think the big qualitative result is that, or not qualitative and quantitative, but like this problem is tractable. I think with the whole series of two level RL and all the moving parts, you kind of many reinforcement learning people might think it's just like completely intractable. It does not really make like, but it's very clear that the techniques that they use kind of like made this problem converge into strong results. Some of the interesting qualitative results are the macroeconomic phenomena that they kind of uncovered. The first one I think is like specialization. We'll touch on this like by going through the plots in the paper in the next few slides, but kind of the fact that because agents have this private quantity of their own build skill, basically we see over time that agents with high build skill tend to kind of become builders versus agents with low build skill become gatherers and just gather resources to sell on the market. The second point, basically disincentivize of agents to work with quality increases. This is kind of like what you touched upon with the equality productivity trade-off. Kind of like in the free market, agents were like wildly productive, but then there maybe wasn't this sense of like equity versus like as you kind of increase the tax schedule to maintain a higher level of equity, kind of the productivity drops off a little bit. So that's like a very cool emergent behavior. And then this last bit is that agents do learn how to game the tax system, just like we do in the real world, through kind of like splitting rather than doing all their labor and like putting all their income into a certain year, but kind of spreading that out over multiple tax years. Another part, some interesting results for sure, are kind of like the mechanism robustness and adaptability. I think even in the face of this tax gaming behavior, we're still able to maintain high levels of social welfare. And then also the interesting emergent behavior is kind of like the paper talks about two different environments, I think split world as well as the actual 4-quadrant, and kind of how the AI economist adapts to even environment-specific differences, which is pretty interesting for the real world, given that a lot of different, like, for example, local counties in the area will have like different structures, different economics, which makes it kind of like more adaptable and promising. So looking at emergent behavior, kind of like the most interesting bits of this plot are kind of this middle one and this bottom right. So this middle shows kind of the how much labor an agent takes kind of like over cumulative labor over a number of episodes. And so you can see that kind of their build skills are like colored, and we very clearly see that like high build skill agents kind of heavily invest more into labor and like generate most of their income through labor. Plot C kind of shows the resource flow, basically who is exchanging what. So if income is going to an agent, what are they receiving for it? And then we can again see the same thing, or a similar theme, where agents with high build skill are kind of sending income in exchange for resources, versus agents with low build skill are kind of just always choosing to send resources out and become gatherers.
So I think one thing that could be interesting here is to see if in this setup there could possibly be an agent with low build skill that still becomes the richest, right? Which is what happens all the time in the real world.
Some more interesting emergent behavior, I think just basically, this kind of just hammers home the theme, but basically this shows kind of the colored squares show kind of like the houses being built by their respective colored agents. And again, you kind of see this theme of like these high build skill agents kind of choosing to build more and like have generate most of their income this way, versus you see very few like actual houses being built by agents who aren't skilled in it. So like again, another good example of like agent specialization. So going to the point about comparing this against like kind of the known baseline bits that we touched on in the like environment section before, but here we can kind of see the levels of social welfare as well as kind of the derived tax schedules, and comparing them to the free market system, the U.S. federal tax schedule, the size formula, and our own AI Economist. So for plots A to B, you can see that this is in the one-step economy. This is where we run one step of the agents and one step of this tax planner. We can see that we kind of recover a almost equivalent social welfare solution to the size formula. And so you can also see like this shows the kind of the marginal tax rates as well as the actual brackets. And we can see that the AI Economist and the size formula kind of recover almost the same thing. And so the authors use this as like rationale to say that like, because in this one-step solution, we've recovered this kind of like optimal analytical formula, then our results must somewhat extend for this like 4 to 10 agent multi-step economy system.
And then I think it's also important to note that the AI Economist and size formula, they actually tax the people with lower income more, which I think is kind of unintuitive, at least for a liberal. So yeah, it's kind of interesting to see that's what it does.
Mm-hmm. And so now going through plots like C and D, we see the two measures of social welfare that they optimize for and kind of the performance of these different baselines against them. The stars on this plot, just the slide unreally detailed, basically shows statistical significance. You can see in the one-step case, like there wasn't statistical significance between the size formula and the AI Economist, but like even in all of these cases where the AI Economist is significantly beating all other baselines. And so those are kind of plots C and D. I think the interesting plot is F, where you can kind of see what the authors mentioned about this equality productivity trade-off, where the productivity is kind of maximized in this free market scenario where it's like at its maximum, and then the AI Economist is all other like taxation mechanisms kind of like are not able to achieve this level of productivity, but the AI Economist kind of comes close. And so that's another result we found like extremely interesting and like kind of captured in the realism in their simulation. Some surprises that we found compared to economic theory. I think one of the big bits, specifically for the left figure, we kind of see that for the left figure, we kind of see the differences in the tax schedules that are actually learned. We can kind of see that some of them are not super intuitive, right? I think specifically the AI Economist choosing to tax like middle incomes most seems like maybe there's like some qualitative explanation for it helps like create a barrier to reduce gaming, like maybe a threshold in which you're trying to like split your income and try to reduce that behavior. We just found that very interesting as it's so different from kind of most tax schedules are progressive or regressive, either increasing with higher levels of income or decreasing with higher levels. And so this is kind of like a new behavior, kind of similar to what Eddie talked about in the RL bits on like this like move 37 was it? And so on the right side, we kind of, this bit is more towards comparing the AI Economist to the size formula. Basically, this discusses how the kind of trading behavior of like high-skilled agents like even affects the behavior of low-skilled agents. Basically, the distilled version of this plot talks about, or like explains that even though low income agents who aren't even affected by like high tax brackets, even in the face of those adjustments, then the subsequent downstream effects affecting these high income agents then also affect these like lower agents. And so some assumptions like in the size formula how of like agent interaction, kind of the authors discuss how this like kind of does not follow, just because you have to actually be considering agent to agent and like even second orders of interaction. Yeah, so I guess like our final slide, kind of just a final discussion points, I guess, for the first question, kind of like what became more realistic and like what gaps do you think still exists in this paper?
So going back to the earlier slide,
Mm-hmm.
so like, for example, like in a lot of mechanisms, then there's like these kind of axiomatic things that you want to satisfy, not for like utility maximization reason, but because like you want to make sure that this is actually some like individually rational, or you can actually self-distribute. For example, in like contracts, you want to make sure that it's like marginal and stuff.
Mm-hmm.
So in tax schedules, it could be like one of these things where you want to ensure that like the marginal tax rate is kind of this marginal structure. So as you make more money, you should get taxed higher because it's like, kind of is palatable to people when you can actually sell it, right? So do you think like this sort of AI economist approach can also accommodate these sort of like axiomatic structures that we want to put on top of the policy? Like you want to maximize policy with respect to some like axiomatic constraint or like some other constraint because of like these practical reasons.
Mm-hmm.
Yeah, so I think you could do this in two ways. Either you impose a hard constraint, so you have the policy output in some like, constrained action space. Or second, you could like put a Lagrangian and then just have like a soft thing on the loss. Yeah, so for sure you can do this kind of thing.
Also, just to answer the question, I mean, this is a pretty simple economy that it simulates. Like, there's so many other agents, I guess, in the economy that have different incentive structures. I was just reading through this paper, I was excited about the results, but also a little disappointed that we're so far away from developing mechanism design using AI for social good. Like there's just so many more things that need to go into this. Like it'd be cool to bring in like business owners as an additional agent instead of just individuals that are being taxed, like including corporate tax in this.
So yeah, there's more people in this room than there are agents in this room.
Yeah.
Right.
So just like even the number of agents.
So can I ask you then, like, what do you feel like are the biggest barriers to getting there? Why do you think they weren't able to do that?
I mean, it's computationally difficult to presume to
Okay.
add more agents. Also, like, I think economic theory is really well defined between the relationship between the government and the individual. But as soon as you start adding the complexities of the real economy, economic theory itself is like not as defined, and so and this paper relies a lot on the says model as like a baseline to compare to. So I think two things. I think one, economic theory needs to advance further, and then two, it's computationally difficult.
Did you want to pick a point?
Yeah, so I think going exactly along that point, like, so I think like in micro, which is the kind of stuff that we've been talking, all the things kind of make sense, and people are rational, or they have some slight bounded rationality model, they're incentivized to act in a certain way, and you can make these nice, mechanisms for auction or contracts and things like whatnot. But I mean, I'm not an economist, I don't know, but as far as I understand, macro is not simply the limit as n goes to infinity of micro. Because if that was the case, then like it would be quite simple. But it seems to me that in like macro, there isn't like all of this like axiomatic approach, but there's a lot of like there's a lot of theories like Keynesianism or like Rawlsianism, all these like different ways of looking at it.
Yes, so I think the reason for that is exactly what we've been touching on, this emergent behavior, right? Like you get these things that you cannot predict with smaller systems. And then so back to what you were saying earlier, I think compute is definitely part of it, but there's also like a more philosophical question, and this is regarding like whether or not we need more economic theory. So, and this goes back to like, I guess like just like deep learning as a whole, right? Which is, we want to model the world, that's our goal, and we kind of have like two ways to do that, right? We can sit down and then think about all the priors that we have in our head, and then create something from first principles, which is what economic theory tries to do. Or we could, use deep learning and then have a black box that like does a much better job than our clear-cut, discrete things, but now we can't analyze and interpret it. So I think really the most important thing is if we can somehow marry the two and get the best of both worlds, right? So like if someday we can have a deep learning system that can go and model these like extremely complex interactions that we couldn't derive from first principles, but then translate that into a discrete structure that we could analyze, then now we get both, right? We get both interpretability as well as complexity. And I think this is something that is actually possible because we're trying to get LLMs to generate code, which is like, I guess, the first step towards this. And then if you're interested like in this line of work, there's also GFlow nets, which Benjo is working on now. So I think in the future, like we can really extend the complexity of this if we have some sort of deep learning system that can go into a discrete structure that we can still analyze. And so we would have like a deep learning system that learns about the world, like how the world works, and then outputs like a more realistic model, and then we use that model and then optimize with like this current structure. So I think there's really this question you have to answer about like, do you want to go from first principles or do you want to go from deep learning? And maybe there's some path in the future that has like the best of both worlds.
Yeah, I just want to add to this point. I think I really agree with you what you said, like, and I think like the optimal solution definitely like the balance between like deep learning perspective and like the principle like from economics. And I think like the need for economics is more like I don't want to use that numbers of data. As you mentioned, like I don't want to use like 10 million, like 100 million years to collect all the data I need. Maybe like there should be a shortcut which is like economic principles. And just want to add to like the population thing. I think like we're definitely not satisfied with like this single like indistinguishable like agent setting, like where you only have one network for all agents. And I think like one thing I've seen before, like in economic theory, some of them use the mean fielding to model like the strategic interaction between like the really big population. So basically the idea is like you divide the population into groups and like each population has some distribution and each one has like different characteristics. So it's more like a generalization of traditional game theory where you have like finite players, but in this scenario you can have like basically infinite population, which is more similar to real life scenario. So I think maybe replace the single agent RL for like the agent side to a more like mean field stochastic game that makes more sense to people.
Thank you.
So I also want to add a point that up to this point I'm still not convinced that this is a good modeling for taxation, even in the simple setting. Not to say more complicated socioeconomic science. So basically, in addition to what have been covered before, I think it's pretty much unclear whether the dynamics will converge to a single point or if different training interactors will lead to different outcomes. Because in a multi-agent game, it's likely there are multiple equilibria and maybe different training dynamics will lead to different outcomes. And on top of that, in human world, we are like also in a game against the government. So as we play, we build up competencies, we build up rules, and we tend to play by the book, and we form sort of convergence toward the equilibrium. But if you just throw out a new taxation policy, people do not know what is the book. People do not play by the book. They may do. They may do things different from what they are thinking that an RL agent will do. And then things might be totally different from what you would expect in simulation or experiment. So that's my concern. So it's not there's not a very clear and unique solution concept that is in this setting, and I just propose a single answer from a single simulation that is not convincing.
Is it important to have a unique solution concept?
Yeah, and also it doesn't consider collusion between individuals. It's like a big defect for real world implementation.
Can I just ask one question as a follow-up to the discussion so far? It seems that we're really thinking about that the first principle economic theory models are important for this setting. Why do you think about that? Because the argument seems to be that, oh, we need to bridge this two, and we really want to go back to that or we want to have simpler models, is interpretability, transparency, or something that's
Yeah. I guess I kind of assumed that in my response, that it's important to bridge the gap.
but why is that?
Yeah. I guess it's kind of related to Yang's point, which is predictability. Like using this kind of methodology to land on an optimal tax policy involves some amount of randomness, and again, we don't know if the parameters of the model, like how much that affected the optimal tax policy. But what's nice about economic theory is that it has a story to it, it's consistent, and it is like peer reviewed. A lot of people have thought about it, and it allows for some predictability. That said, a lot of economic theory is based on a very limited set of assumptions, like very constrained assumptions that are not always true. Like assuming that people are rational is not a fair assumption to make. And this paper does that as well, but in economic theory they assume that. And so I think that even if it's consistent, it can be wrong. So like the accuracy is off, but it's precise with economic theory. So yeah, maybe it isn't important that we use it. It seemed pretty important for this paper because that's what they compared. Like that was the baseline that they compared results to.
I mean, I personally feel like I agree with a lot of what you said, but I think when it comes to using AI to design things like broadly speaking public policy, I think it really misses what public policy is and how it's designed. Like, it's not like the U.S. Congress is going on thinking, okay, what is the way to rationally maximize utility for all American citizens, regardless of my term limits, regardless of my political affiliation, regardless of what.
But maybe that's what it should be.
They should. I'm not saying they shouldn't. I'm asking, are they incentivized to do that, right? Like
They're not, but maybe it's a better model than that.
Right. I think so. I agree that this, like, it is better if you're trying to generally maximize social welfare, but public policy generally, especially tax policy, is an extremely divisive political tool. It changes every 4 years. And a lot of these changes aren't rationally justified. So it's not that agents are rational. I don't even know if policymakers are rational with respect to welfare maximization.
Can I ask, are you currently satisfied with our government? So this is like, I think, a potential improvement. Because now you can guarantee that the planner doesn't have these other incentives, right?
Right, but can you convince someone to actually take this up? Is it in their incentive to take this up?
So if you frame it as this is a way for you to gain more power and get a better term, then maybe, right?
But that's not what it's maximizing, is it?
Sorry, go ahead.
But that's not what this is maximizing. This is
No, that's a completely different discussion. Yeah.
But I think there is a lot of room for AI-informed policy through mechanism design. I'm just thinking on like the smaller scale, the municipality scale, when things are less politically heated. I think there's a lot of room for that. And I do imagine a world in which senators refer to what the Economist says, like what it concludes. I don't know if this is like inherently not practical.
So can I ask, how good is current macroeconomic theory for predicting? It's very bad, right? So here's the thing. This is one opinion. I don't know if I hold this opinion, but it's one opinion. You could argue that the only thing that matters for a model, evaluating a model, is its predictive power, right? If it's good at predicting, it's a good model. If it can't predict, then it's a bad model. And our current models are terrible, right? So there's a lot of room for improvement, and I think that deep learning can do it, based off what we've seen in the past. So to me, it looks a lot like current economic theory looks like what feature engineering looked like in 2003 or 2006, right? And then deep learning just like blew it out of the water. So I see like a very similar thing happening